The second part of this lecture, we're going to start out by talking about period and frequency. Periodic motion is a motion that repeats itself at regular time intervals, and we sort of discussed this a little bit in the beginning when we talked about the ruler bouncing back and forth. That is a form of periodic motion. When you think about things like pendulums and balls that bounce up and down on a spring, that is more what we have in mind when we talk about periodic motion. So the period in a periodic motion is the time to complete one full oscillation, and it's generally abbreviated capital T. So you start from a position of rest, the motion goes through its entire cycle, and when it returns to that rest point the first time, then that is called a period. And the time it takes to complete that is called the period. Now, it might go down, pass through the equilibrium point, go up, and then come back down. It's when it comes back down that second time that you actually have gone through one complete oscillation, and that's the time that it is to complete one of those is a period. Frequency is that period divided by, is the reverse of that. It's the 1 over the period, or 1 over t, and it's generally abbreviated little f. And it's the number of events that can be completed in any particular time interval. So if it's a second, it's the number of events that can be completed in a second. If it's a minute, it's the number of events that can be completed in a minute. So here's an example of a simple harmonic motion. Simple harmonic motion, you start at a rest point. First of all, simple harmonic motion is oscillatory motion in a system where the net force can be described by Hooke's law. Okay, so the net force that occurs is described by Hooke's law. The amplitude is the maximum displacement from the equilibrium position. In this A here, the equilibrium position is right here, x is equal to 0, and big X represents the amplitude. So an object that's attached to a spring slides back and forth on the surface. When it displaces its maximum displacement in one direction, that's the amplitude, that's A, or X, excuse me. It comes back in B here to the rest position. It then compresses to minus X. It then moves right back out to this point right here. This entire motion, the time it takes to go through this entire motion to this point, back to this point, I'm sorry, since we started here, back to this point is a cycle, and therefore that is the time it takes to get from A to E is a period. And the number of times in a particular time point is called the frequency. So the period in a simple harmonic oscillator or simple harmonic motion is equal to 2 pi times the square root of the mass divided by the spring constant. So whatever mass is causing the deformation divided by the spring constant, you take the square root of that, multiply by 2 pi, and that gives you the period. Obviously the frequency is 1 over that, and so it would be 1 over 2 pi, and then these would be reversed. The easiest way to do it is to calculate the period and then take 1 over that as the frequency rather than doing this big calculation here. So let's take a look at a problem. Shock absorbers in a car go bad, the car will oscillate at the slightest provocation, such as a bump in the road. Calculate the frequency and period of these oscillations for such a car if the car's mass is 900 kilograms and the force constant is 6.53 times 10 to the 4th newtons per meter. So in order to do this problem, let me write down, first of all, the period is going to equal 2 pi times the square root of m over k. So it's going to be 2 pi times the square root of 900 kilograms divided by 6 6.53 times 10 to the fourth. And if we do the math in this situation, we get 0.0866 seconds. The frequency is equal to 1 over the period. It's equal to 1 over 0.0866 seconds. And that is going to be 11.5 oscillations per second, or hertz. A hertz is an oscillation per second. So in this situation, all you have to do is do this calculation first and then take 1 over that, and that gives you the second number. Here we have a paper that's used to look at a harmonic motion. You have a mass here that's initially deformed a certain amplitude, and then it's allowed to oscillate. And the paper travels, and there's a little pin here, and it makes what looks very much like a sine wave. Matter of fact, it is a sine wave, and it's described by a sine function. So here we can graph 3 different graphs here. Okay, we can graph the position of the ball. Here's the oscillator here. Here's the graphs that are being drawn, and we can graph the position at any time point. We can graph the velocity at any time point, and we can graph the acceleration at any time point. And when we do that, in all 3 of these situations, we get these various sine waves. The initial position of the vertical displacement, the maximum value is x. Velocity is initially 0. It's negative as the object moves down, and positive when it moves up. Now the formulas involved here are given right here. The position at any point in time is given by the amplitude times the cosine of this value right here. 2 pi times whatever this time is divided by the period. So the equation that describes this cosine wave here is given right here. The velocity at any time point is equal to the maximum velocity, a negative maximum velocity, times the sine of the same evaluation, and this is right here. Notice you start in a cosine wave, you start at x, the amplitude, and a sine wave, you start at 0. Notice that because this is negative, this begins with because the velocity is negative, it begins with a downward deflection and then upward, etc. And then lastly, the acceleration is described by this, which is also a cosine function, and it's shown right here. And notice that it's also negative, so it starts down here and proceeds in this way. And notice x here is the maximum amplitude, k is the constant, spring constant, and m is the mass. And these are the 3 formulas that can be used to describe these 3. And actually, this mathematics is gone over in great detail in the pre-calculus math course, and if you've had that class, you may remember this. So here's a problem looking at this new stuff. Here we have a baby in a stroller, and you know this is one of those bouncy strollers. So the spring in this bouncy stroller has will stretch 2.5 meters with the baby in it, and has an 8 kilogram baby. So what is the spring constant in that situation? So again, this follows Hooke's law. So F is equal to Kx minus Kx. So K is equal to minus F divided by X, which is equal to, this is an 8 kilogram baby times 9.8 divided by 0.25. These springs tend to not be very strong. K here is going to equal 313.6 newtons per meter. The second question here is, what is the time for one complete bounce of the child? So now we have the period, one complete bounce, is equal to 2 pi square root of m over k. So that's going to be 2 pi square root of 8 divided by 313.6. And if you do this math, you get 1 second. And so 1 over that is the frequency is also 1 second. What is the child's maximum velocity if the amplitude of the bounce is 2 meters? In order to do this, you have to know that the potential energy of the elastic potential energy of the spring is translated into kinetic energy, like we talked about before. And so that means that 1/2 kx squared is going to equal 1/2 mv squared. And x here is going to be this amplitude that we just talked about. So 1/2 times 313.6 times 0.2 squared has got to equal 1/2 times 8 times v squared. And if you do the math here, v is going to be 1.25 meters per second. So the maximum velocity here is 1.25 meters per second. Let's talk now about the second type of oscillator, which is first one there we were talking about was a simple harmonic oscillator. The second kind is a pendulum. A pendulum is a form of simple harmonic oscillator that has a specific setup. A simple pendulum is an object usually of small mass. This is known as the pendulum bob, and it's suspended from a wire, as shown here. And you have L, M is the mass, etc. If you do the calculations here, it turns out that the period, the time it takes to go from here over to here and then back, is equal to L over G. Now what that tells you is that it doesn't matter what the mass is here, as long as it doesn't break the string, that the period is independent of the mass that you hang on it, which is why when you adjust a grandfather clock, what you do is you move that bob up and down, and that changes the speed with which it rotates back and forth. It also so it tells you it's a function of the length and the gravity. So here again, T is the period, L is the length of the pendulum, which is from the attachment point to the mass, and G is gravity. So let's look at a couple problems with this. The first problem states that how long does it take a child on a swing to complete one complete swing if the center of mass is 4 meters from below the pivot? Okay, we're on Earth. We'll assume we know that we're on Earth. So P is 2 pi square root of L over G, 2 pi times the square root of 4 divided by 9.8. And if you do that math, you get 4.01, let's just say 4 seconds. And if you put, it doesn't matter how big this child is, as long as it can take the weight, as long as the swing can take the weight and it doesn't cause big problems. The second problem here states that you have a clock, a pendulum clock, a grandfather clock that moved to the moon, where the acceleration is now 1.63 meters per second squared instead of 9.8 meters per second squared. And the question now is, how much time does it take for the hour hand to make one full rotation? So how much time will it take to get, if it's 12 hours on the Earth, how many hours will it be on the moon? And we know that the period on the moon divided by the period on the Earth is equal to this formula twice. We'll put the numbers in, since it's going to be the square root of L over the gravity of the moon divided by 2 pi square root of L divided by the gravity of the Earth. If you keep doing this, you see that obviously these cancel out and the L's cancel out, and you're left with the square root of 1 over m and 1 over g, which you can take the 1 overs away by just reversing them. And so you put 9.8 divided by 1.63 square root, and that ends up, it's 2.45 times faster making the loop around. And so if it takes 12 hours on the Earth, it will only take 4.9 hours on the Moon with the same length. If you make the denominator smaller, or do I multiply that? Did I make a mistake here? The period will be shorter if the denominator is larger. So actually I should multiply it. So I should take 12 times 2.45, which is going to be about 30 hours, something like that. Let's finish up very quickly with the transformation. It says that we have energy in simple harmonic motion. The transformation of energy in a simple harmonic motion is illustrated above. And what you have is that the sum of the kinetic energy generated here as this moves back and forth, and the potential energy, elastic potential energy, is equal to a constant. So the sum here, depending on where you are at any point, is going to be a constant. So 1/2 mv squared plus 1/2 kx squared is a constant. And so 1/2 mv squared plus 1/2 kx squared is going to equal, and it turns out, if you do the calculations, that this equals 1/2 times k times the amplitude squared. The maximum velocity in this situation is equal to the square root of k over m times the amplitude. And with a pendulum, the maximum angular velocity is equal to the square root of g over L times the amplitude, which in the case of this is the displacement in radians. So let's finish up. We have one more problem to do and then we'll be done. Suppose a car that is 900 kilograms and has a suspension system that has a force constant given here. The car hits a bump and bounces with an amplitude of 0.1 meters. What is the maximum vertical velocity if you assume no dampening? From the formula I just gave you, Vmax is equal to the square root of k over m times the amplitude. So this is equal to the square root of 6.53 times 10 to the 4th divided by 900 times 0.1. And if you do the math here, you get 0.852 meters per second.